Hello and welcome. This is section 5 of chapter 13 on gravitational potential energy. And it's a really core topic that builds on not only Newton's theory of gravity, but it's also a good application of chapters 9 and 10 on work and energy. So we have the equation here. It would be worth a couple minutes just to go through and verify where this thing actually comes from. So on the left-hand side of this equation here, I'm going to be writing that recall from chapter 9, or rather chapter 10, that gravity is a so-called conservative force. And that any conservative force is one, there's several definitions, but the one that's helpful to us now is that the force can be expressed as a function of position. So the work done by a conservative force, you can integrate it, right? And it's just a resulting difference in the integrated values, which is minus the change in some function, right? The definition of work is the integral from some initial to some final value position of that component of the force along that axis. And so from this, you can obviously show that the negative of this integral gives you the potential energy function. And so if we take the value of the gravitational force law, integrating that, f sub r dr from r initial to r final, well, along the r-axis, it's towards the center, or towards the origin, so it's minus g big M little m over r squared dr, integrated from r initial to r final, and so there's lots of negative signs to keep track of here. The integral of 1 over r squared is minus 1 over r, and so that's going to cancel with this one. And so we'll be left with the r final at the top and r final at the bottom. It'll be g big M little m. Well, we need more room than that. Down here, perhaps. Yeah, big G little m big M. I'll just write them on the other side, times the quantity 1 over r final minus 1 over r initial. And so those quantities give you the change in the potential energy. And so that defines the potential energy function. I guess we use a capital G subscript for gravity. Sometimes we use G, lowercase g. So one thing to observe about the potential energy is that it's a negative quantity. What does it mean? We technically need this definition this negative sign comes from the fact that our reference point, and this might be a little bit strange from considering other problems that we've had, we set the zero of potential energy at r equals infinity. And when we set the zero equals to r at infinity, then this function in the middle here represents the difference in potential energy between 0 and our spot. It's always decreasing. And technically, for point masses, as r goes to 0, the potential energy goes to minus infinity. There's not objects that have a 0 dimension, and so that's only theoretical. And so if we look at the curve in the next slide, then we'll see that as that same feature that we're looking for. There we go. It's got the 0 on the far end, and the closer you get to the planet, which, by the way, we're assuming that one of the planets is at rest. If you're assuming that they're both moving towards one another, you have to adjust by a few constants, but it's still the same thing. R at infinity, R is and r equals infinity, potential energy 0, and it's increasing, or it's decreasing, which would make the kinetic energy increase, because in these situations we usually set total energy to be constant, and so the decrease in potential energy, making it more negative, will give us a positive kinetic energy. And again, as you go to negative, as you go from R equals to 0, technically potential energy goes to minus infinity, but you'll never get there. I mean, eventually you'll get to the point where you crash into the planet. Like if you have a comet or a meteor heading towards Earth, you know, ignoring a drag force, as it gets closer and closer to the surface, the potential energy is going down, kinetic energy is going to go up, but eventually it will reach the point of the actual, its position is actual the radius of the Earth. And so it'll be a potential energy that never decreases because it's not going to tunnel through the Earth. And so this part after or inside this value of R is physically irrelevant. Even if you were to, say, tunnel a hole through the Earth so that the meteor could just, you know, without atmosphere, that the meteor could just fall towards the center of the core of the Earth through some magic tunnel, even this still wouldn't be the correct way of describing the potential energy. You would need a different formula to describe it. That's not a problem we addressed here, but in physics 2, you learn the tools you'll need to handle a problem like that. So that's interesting. Moving on. And so right here you see an example of what's going on for like a horizontal object as it's, so if it's released from rest, this straight line right here represents the total energy. So when it's released from rest, it starts out with a negative potential energy. The before, you know, this is a before and after pictorial representation that you learned in chapter 9. The total energy of the block, really of the system, starts off as negative, and it gets more negative, which allows the kinetic energy to get positive. And so that's how we go down the energy diagram. This is a confusing energy diagram, I think. So going back to section 10, section 10.5, I think, or to 10.6, has a whole section related to energy diagrams. And so if you go over the basic ones, it'll help you with this more complicated one, because this one's about as complicated as you get, at least in physics 1. So a classic example, which I will briefly mention, I would highly recommend that you try and work it out on your own, would be escape speed on a certain planet. So they have a 1,000-kilogram rocket launched from the surface of the Earth. If you talk to someone that works in that space industry, you'll see that rockets are usually launched more closer to the equator because they already have like an inherent motion to it by their rotation. If you launched a rocket from the North to the South Pole, it's not in the reference frame of the rotating Earth, it's not moving at all. But near the equator, it's moving faster. So it's less fuel to get it to this speed. But the energy considerations of escape speed are that you start out, so you have the big planet, mass m, radius r, and you have to start. Now, you don't obviously start on the ground with a very large velocity, but I mean, you start at rest and you use the thrusters to build up this speed very quickly, still at a distance that's close to this initial radius of the Earth. And so we're going to say that it has a kinetic energy. What's its total energy at this beginning spot? It's going to have a 1/2 mv squared minus, it's going to have a negative potential energy of minus g big M little m over radius of the Earth or the planet. Again, the rocket or the object has its mass little m. Now, what does it mean to escape the gravitational pull of a planet or of a star? We're going to model that as saying that when you're infinitely far away, you're at rest. And so what's the energy at the far end here? Well, if you're infinitely far away, your potential energy is 0. If you're at rest, your energy is 0. So that means the total energy should equal 0. And so you have to resolve the fact that all of the kinetic energy that you have on the surface as you're moving upward gets converted to potential energy, actually. I mean, that's something that you throw a ball up into the air, kinetic goes to potential, but in this case, it goes to potential, but now your final potential is zero. And so now that zero means you're stuck here. And so now at this point, you're obviously free to fire your thrusters, which will do work to increase your motion in some other direction. You can start exploring the interstellar space, or interplanetary space or whatever. Yeah, interplanetary might be the proper term. So that's escape speed. You can certainly read through this problem and find out for Earth, what the escape speed is. It turns out to be independent of the mass. So if you set 1/2 mv squared equal to cap g, big M, little m over radius of the Earth, you find that the escape speed equals what? V sub ESC equals, well, the little m's cancel, and so it ends up being square root of 2gm over r, square root 2 capital G capital M over capital R. And so you can look that up, do that calculation to calculate the escape speed of different planets, and pretty curious. We can go ahead and look what answer they get here. Oops. There's that answer. Oh, they're still in the visualize step. So they get an escape velocity of 11,200 meters per second, 25,000 miles an hour. Typical space units for velocity are kilometers per second. So 11 kilometers per second is the escape speed on Earth. A note for when you're plugging these things into Mastering Physics, please use the numbers in the book. There's a table of astronomical data that's here somewhere. Should be in the slides here, but it's certainly in the textbook. Please use the numbers in the textbook. A funny story about that: one semester I was teaching, and there was one of these problems where you had to look up data for Jupiter, Neptune, or I think it was, you had to find freefall, acceleration to freefall on Jupiter, I think. And the student in class says that he looked up the values of the mass of Jupiter and the radius of Jupiter on NASA's website, the actual computed data on website, and he plugged that into his answer, and Mastering Physics counted it wrong, actually. And he plugged in the values that the book gave us, and it was right. And so there's several remarks to make about that. On first thought, that might seem to just completely invalidate all that we're trying to do in this chapter. But if you think about it, the measurements of the free fall on Jupiter, actually, I think he actually looked up it on the computed free fall on Jupiter. He got, those values measured cost hundreds of millions, if not billions of dollars to find out. And what's great about these quantities is that most of them can be found to a good, within 1% by just simple telescopic observation. So it's certainly saying something to the basic nature of these calculations that we do. So yeah, there's a picture. Can't seem to clear all my drawings for some reason. Okay, so moving on. That's one classic example to consider. The other one is a sort of atomic or sort of planetary free fall problem, where we're just kind of releasing an object from rest. This is a little explanation of how we resolve gravitational potential energy in this section with gravitational potential energy, as you know from a previous class. And it's worth going through this derivation, because on a flat Earth approximation where the distance is much, much less than the radius of the Earth, Well, what you do is you have to break up the expression and do a little calculation. Oops, go back. You have to do a little calculation here where you take r plus y and so-called probably factor out. The book goes through it, but you would factor out the r from the denominator here. So this would be minus g big M little m over r times 1 plus y over r, and then expand this in terms of y to show that it equals m times g times y, because this this term then gm over, well, you need a r squared. Factor out r squared here. And that'll give you a way to do it. So there's a way to connect the gravitational potential energy in this chapter with the gravitational potential energy on chapter 10. You just have to use a approximation, approximating this. You're approximating this function right here as an expansion in powers of y. Good. So that's how you do that. And then we have one final example. I think I'll just let the readers go through this example on their own, but just more practice with resolving these two expressions for potential energy. One common example is also to say drop a massive object very high up above a planet and redo the free fall problem. That's another good practice problem. But that is the conclusion of this section on gravitational potential energy. We will finish in the section 6 on orbits, and there's some further energy considerations in orbits. So until then, as usual, thanks for your time. We'll see you back here at the next video. Take care.